want to talk about another concept here. And again, what we see here is your function, your f of t, or your inverse Fourier transform. Let's just work with the cosine omega, let's just say omega naught. And this will be our fundamental, angular velocity, or 2 pi fundamental frequency times t, and equals, this is the Fourier transform. So this is your Fourier transform, and this is your inverse Fourier transform. Okay? Also, what we have below, your delta Dirac function at t, and this is the Fourier transform for that, or f of w, or f of omega. Okay, so what happens if we add the two together? So let's just write it out, plus omega, or delta Dirac of t, no time delay. Well, if you recall, the Fourier transform is linear. So what does that mean? It means that we can distribute it like so. So linear operator, so as a result we can do that. A lot simpler now, right? Because we just broke it up into these two components, which we already know. Now, if you guys were with me on the last video, we already went over what cosine is when you graph it, right? So let's just graph cosine. So cosine at omega naught, right here, and negative omega naught, we aren't multiplying by anything. If we were multiplying by something, then say it was like 2 cosine omega naught t, then it would actually be 2 pi. If it was 4 cosine omega naught t, then it would be like 4 pi multiplied by this whole thing. But we're just not doing that. It's just 1. So it's 1 over there. Okay? So it's pi and pi. Right? And this is, again, this is your amplitude density spectrum for this cosine. Okay? Easy enough. So what's the amplitude density spectrum for this term? Again, very simple. It's literally just 1. So right? So now what happens when we add this and this together, or this graph and this graph together? Well, so here, pi plus 1 at negative omega naught, and everywhere else is just 1. Boom.